Sir, good morning.
Sir, if you can send soft copy.
Pazhanivelan sir, very good morning.
Sir, good morning, sir. Good morning, sir.
Yeah.
Can we go ahead, sir?
Yes,
Yeah.
sir.
Yeah.
Yes, sir. Sir, with the permission of director, sir, Sundaramji, can we go ahead?
Yeah, go ahead. Let's start it. I think 50 people, more than 50 people have joined.
No, people are joining, sir. We can start, sir. Okay. Very good morning to everyone. Let me welcome everyone for this Bharat Ka Amrut Mahotsav webinar. And also it is jointly organized by Indian Institute of Rice Research as well as Society for Advancement of Rice Research. I have seen many esteemed scientists in the as a participants, and I am also expecting many more to join during this presentation. And we are also recording our presentation, sir, because it is very useful for our rice scientists, and we will be also sharing this presentation, this one to everybody. I welcome you, sir, for readily accepting for our request without any hesitation. I thank you very much, sir, for Dr. Sundaramji. Actually, I had his presentation in one of the webinars, and I found it very useful for our rice research. Then I immediately asked, immediately sent a message, even webinar itself. Then he's readily agreed. Then whatever whenever you ask me to give a presentation for rice scientists, he was ready to give it. Thank you very much, Pazhanivelan sir. I would like to thank our director and welcome our director, his honorable director, who has taken a lot of changes in our IIR working environment, and is also encouraging all the people like our different committees, and we are able to do it with your encouragement, sir. I also welcome our earlier directors, Dr. SARR and many more rice scientists across the country. They are working in different places, and I welcome you for this special webinar, and we will be definitely benefited by your presentation, sir. This our whole program will be after my speech. Our director will give initial remarks, and then Dr. Akshay, who is our plant physiology scientist, he will be introducing the speaker. Then after your presentation, sir, our D.V.K. Nageshwara, who is our principal scientist in soil science, he will be facilitating question and answers, and a few question and answers where we wanted to collaborate with you. Then there will be closing remarks by our director. This vote of thanks by my colleague, Dr. Sanjay Saha. This is about our program, sir, for the benefit of the participants. Now I request our honorable director, Dr. Sundaramji, to say a few words before Akshay takes introduction of the speaker. Dr. Sundaramji, how it is.
Before we move further in terms of today's proceedings, I from the family of Indian Institute of Rice Research, and also from the family of All India Coordinated Rice Improvement Program, and also on behalf of Society of Advancement of Rice Research, I offer a warm welcome to Dr. S. Pazhanivelan, who is here to give an inspiring speech on the topic rice area mapping and yield estimation, assimilating remote sensing products with crop growth models. As you all may be aware, there are two tools or techniques which are being increasingly used for forecasting, assessment, and then other works. One is, of course, remote sensing, wherein India has made a significant headway. And another is crop growth models. Particularly, there are several models like Oreza model and all which are being used. And one of the important questions we get every time from Parliament and also from our superiors in ICAR is how much area is under each variety. That's a big question. And also how much is the total area in a particular state or in a particular district or regions. And I hope as part of your talk, you'll be dealing with these questions also. And I'm sure that today's talk will be inspiring many more people to take up this advanced area of remote sensing, and also refine our thought process with regard to crop growth models. Sir, as you may be aware, we also have a set of scientists working this particular frontline topic, particularly with regard to remote sensing and also crop growth models, led by Dr. B. Sailaja. And I suggest that our team can later have a one-to-one interaction with Dr. Pazhanivelan so that we can tap into his expertise, and then we can even submit for some joint project proposals to funding agencies. I now request Dr. Akshay to introduce the speaker. Thank you very much, Dr. Pazhanivelan. Thank you for the opportunity.
Hello, am I audible?
Yeah, yeah.
Hello, good morning all. This is my privilege to introduce such a illustrious agronomist, Dr. Sella Perumal Pazhanivelan. He is specialized in remote sensing application for agricultural applications, including crop monitoring, soil and land resource inventory, land degradation, agricultural disaster management, and monitoring water resources and agricultural emissions, besides drone applications for precision agriculture. In his 23 years of service, he has contributed a lot for innovative technologies through research projects in collaborations with IRRI, ICRISAT, ICAR, NRC, NRSC, SAC, and Government of India in crop management technologies, salt-affected soils, saline water management, and geospatial output supporting the Tamil Nadu state government and Government of India. TNAU rice technology for crop insurance developed by scientists through multinational public-private partnership project resulted in a quick payout of rupees 3,085 crore as compensation from insurance companies, helping about 7,53,000 farmers, and remote sensing based crop insurance was made as an operational service for the first time in India as a measure of disaster risk reduction. Through satellite-derived spatial drought indices and methodology for flood damage assessment, he ensured drought and flood preparedness and helped Tamil Nadu government to get rupees 1,740 crores as drought relief during 2016 and 17. The detailed information on soil and crop department, soil and crop was for well received by the policymakers in defining government schemes and farmer welfare programs. As head of the Department of Remote Sensing and GIS in TNAU for the last 4 years, Dr. Pazhanivelan is responsible for establishing specialized GIS labs for crop and disaster management, soil and water resources, and drone lab to cater the research needs, as well as developing geospatial expertise through PG program in geoinformatics. At present, he is an expert committee member of DST NRDMS. He is responsible for developing network among scientists in the field of GIS for agriculture, besides contributing for developing geospatial policy and projects at national level. A brief about his educational journey. Born on 27th July 1917, he has finished his MSc and PhD from TNAU in 1994 and 1997 respectively. Subsequently, he has joined as assistant professor at TNAU in 1997, and currently he is serving as professor and head department of remote sensing and GIS, TNAU, Coimbatore. He has supervised about 20 MSc and PhD students and handled about 23 projects. Some of them are like IFCO design and fabrication of customized nano fertilized formulation for drone enabled delivery of nitrogen for improved use efficiency. World Bank project, Government of India RKVY remote sensing project, NRCS developing a methodology and interface for spatial maize crop production estimation using crop simulation models. Then NRSC land degradation mapping in Tamil Nadu. Then IRRI remote sensing information for crops and insurance in emerging economics. Then he is member of expert committee, National Resource Data Management Systems, DST India. He is also member state level coordination committee in crops insurance. He has received several awards. The prominent among it is TNAU Best Researcher Award. He has contributed about more than 100 publications in various journals of repute. So this is the brief introduction regarding respected Dr. Sella Perumal Pazhanivelan. Welcome, sir. I hand over floor to Dr. Mahendra Kumar.
Now I think
Sir, Dr. Pazhanivelan, sir, you can go ahead, sir. Now it is yours. The floor is yours.
So let me share my screen and this. So whether my slides are visible?
Yes, sir, visible, sir.
Yes.
Go ahead, sir.
So respected Director, Indian Institute of Rice Research, the esteemed scientist in rice working across the country. Really, I am very glad to be with you, you people who are serving for the cause, noble cause of farmers. And first of all, I thank Dr. Mahendra Kumar, who has invited me on behalf of ICAR-IIRR for delivering this lecture, because I am basically an agronomist, but I have a lot of passion towards remote sensing and drone applications in agriculture. So whomsoever invites TNA remote sensing naturally shares all the views and expertise with the scientific community. So today I'll be presenting the salient features on remote sensing and drone applications in agriculture, with the special emphasis on rice monitoring and yield estimation, because the group mainly concentrate on rice research. I will also cover upon some of the other natural resource management and other crop research on other crops also for the information and knowledge, and which can be used in rice monitoring also. So Tamil Nadu Agriculture University is a pioneer in establishing exclusive department of remote sensing among the state agriculture universities, and the department was started in the year 2010. But our research on remote sensing applications started in the year 1995. So we concentrated earlier in the mapping of soil resources for sustainable agriculture. So we did the soil mapping at 1:50,000 scale. But now we are in an advanced position. Now we are coming out with the digital soil maps with the use of deep learning tools, integrating the profile information with the satellite-derived environmental covariates. Then the disaster from 2004 tsunami onwards, we are monitoring. Mainly, we are assessing the impacts on agriculture. So the flood in 2015, then even last year 2021, cyclone, the Kaja cyclone in 2018, we have monitored. In case of drought, we ensure the preparedness for the state government. We assess all the drought indices in a regular interval. There are more than 6 drought indices which are prescribed by the drought manual of the government of India. So which comprises meteorological and spectral indices. So we generate all the information for drought indices. Then land degradation mapping. We are part of the National Network on Land Degradation Mapping and Change Analysis. We were part of the first cycle in 2005, and now in the 2015-16 also we have done. So which covers the soil and land degradation, mainly the area under salinity, alkalinity, erosion, and other mining areas, then industrial effluent affected areas. All these things we map. And from 2012 onwards, we are rigorously into crop area mapping and yield estimation. So I am being an agronomist. I have done my PG diploma in Indian Institute of Remote Sensing, then postdoctoral training come research work at McGill University, Canada, then other trainings. We have strengthened the crop area mapping and yield estimation. So we cover wide area of crops, but we have done a lot of work in rice. We have covered all the parts of rice mapping, monitoring, yield estimation, loss assessment using different tools, and we have developed many tools exclusively for rice crop. And we have applied it to the crop insurance also. So Tamil Nadu is the first state to introduce a remote sensing based crop insurance as an operational service, mainly based on our technical support. And the government has issued a GO that all the insurance companies, they should use only the TNA remote sensing data, because we have again and again proved our capabilities and the accuracies. Then as part of World Bank project, we are monitoring the water resources also. So we have digitized all the tanks, that is around 33,000 tanks are there in Tamil Nadu, both the government maintained and the local tanks, and we are assessing their water spread and its availability of water and its impact on agriculture. So now we are going towards the automated irrigation system, not only at the field level, at the command area level or ICAR level, we are moving towards that. Then the latest addition is drones. From 2017 onwards, we are working on drones. We have different types of drones with us, mapping drones of copter type and plane type, as well as the spraying drones, that is for smart delivery of agriculture inputs. We have a hybrid drone, that is fuel operated drone for this spraying purpose. And we have other small drones for with the cameras and the sensors for crop mapping, and the now we are going for the pest and disease mapping, and we are planning to combine all this information into precision agriculture. That is the ultimate idea we are working on. And we have a strong team in the department, as well as we have trained around 20 scientists across the state under different research stations, as well as the KVKs, to support us in collecting the ground truth. Sir, whether my slides are moving?
Yes, sir.
Okay, thank you, thank you. So many of you may be working in remote sensing or might have heard about remote sensing. Just for the refreshing of the scientists, I am touching upon the basics of remote sensing in a very brief manner. So there are two types of satellites available. One is a polar orbiting satellite and the geostationary satellite. Polar orbiting means it will rotate pole to pole, and these are the satellites which are placed at a height of 600 to 900 kilometers and widely used for our Earth observation, including crop monitoring. The second category is the geostationary satellites. They are placed at an orbit of 36,000 kilometers, and they move in a speed, rotate the Earth in the speed as that of Earth, so that it looks like it is stationary and it covers the same area throughout the day. So we get continuous pictures about the objects over the Earth's surface. It is mainly used for telecommunication and weather related things. So for remote sensing, we are using mainly the polar orbiting satellites. Then here the basic principle is we are using the electromagnetic spectrum. So this visible, that is 400 to 700 nanometer, and shortwave infrared. So this we call it as optical remote sensing. So here the sun is the source of energy, and the reflected radiation is captured by the satellite sensors. So based on the difference in reflectance, we discriminate the objects and characterize them, analyze them in detail. But most of our crop activity, agriculture activity, it is done during the monsoon season. So it is fully covered with the clouds. During that time, we will not get images, satellite images free of clouds. So to overcome that, we are using the microwave remote sensing, that is the waveband of 1 centimeter to 100 centimeter. So here we are using the synthetic aperture radar to emit the microwave and capture the backscattered wave. So here the backscattering properties of the objects, which decides basically, which helps us in discriminating them and analyzing them. So in between we have the thermal remote sensing, so which is widely used for water related or moisture stress related works. So this is the basics. So three types of remote sensing: optical, SAR, that is microwave, and the thermal remote sensing, which can be effectively used for agriculture monitoring. So when you take up any remote sensing based research work with the use of satellite sensor, you should have 4 parameters. You should decide about the 4 parameters of the sensor. You should judiciously select the satellite sensor, or otherwise you may not be in a position to satisfy the requirements. So the first one is the spatial resolution. That means For example, 1 meter means in the satellite image, 1 pixel, it corresponds to how much area in the ground. That is called the spatial resolution. That means 1 meter means it will give you the information about the object within the 1 meter by 1 meter size as one basic pixel. So on the other hand, 1 meter means this image or sensor cannot detect the object which is less than 1 meter size. So it will be detecting the object above 1 meter size. So like that, we have different resolution. So depending upon the requirement, for example, this MODIS satellite, it is having 250 meter resolution. With that, we cannot go and monitor the individual field level crop condition and other things. Whereas we can generate the information for the state as a whole. Okay, what is the cropland in Tamil Nadu? What is the cropland in Andhra Pradesh? What is the forest area in Telangana? So like that, we can give generalized information with 250 meter resolution. But if you want to study the individual crop in individual field with variety, growth, yield, then you have to go for very good resolution. That is for agriculture monitoring, 5 meter to 20 meter is enough. Then the spectral resolution, which I have already described, visible spectrum, then thermal sensor, microwave. So in visible, we have many satellite, ResourceSat, Landsat, MODIS. Then thermal, Landsat and MODIS data is available. Then we have the temporal resolution. So this microwave. So the microwave data, which is highly useful for agriculture monitoring, this we should take note. There are 7 satellites available across the globe. So we have access to 5 satellites. That is research from ISRO, Indian satellite. Sentinel, it is from European Space Agency. TerraSAR-X from Germany. Cosmos Comet from Italian Space Agency. Then ALOS Pulsar from Japanese Space Agency. But we are mainly using now the Sentinel-1, which is the open source data. The data is available free of cost. If you consider TerraSAR-X, it costs around for 30 by 30 kilometer one scene, it costs around 3 lakh rupees. So now the whole the European Space Agency as well as NASA and ISRO, to some extent, they are coming out with the open source data sets. That means the satellite data is available free of cost. So with the Sentinel missions, the whole remote sensing world, their research activities are moving towards developing the tools for using these open source data sets. Because earlier, lot of our project costs, it was used for purchasing the satellite data itself. But now the scene is different. Then comes the temporal resolution. That means this polar orbiting satellite from, for example, equator to equator. For one orbit, in case of Sentinel, it takes 90 minutes. So it has a swath of 200 kilometers. In one pass, it will cover 200 kilometer width. So to cover the entire Earth and to come back to the same place, it takes 12 days. That is called the repetitivity or temporal resolution. So once in 12 days only, we will get the image of Sentinel. So we have to, depending upon our requirement, we have to select a satellite sensor with good temporal resolution. So the Sentinel, what they have done, this European Space Agency, they have launched Sentinel 1A and 1B in the same orbit with the same parameter. So we get the image once in 6 days. Like that, the CSK, the repetitivity is 16 days, but they have launched 4 satellites. That is CSK 1, 2, 3, 4 within the same orbit with the same one by one it will come. So once in 4 days we can get to the information. So these are the basic information to decide about the sensor, what we are going to use it for the crop monitoring or natural resource management for any sort of agricultural activity. So we have to go for polar orbiting satellite with the optical, thermal and the SARR remote sensing system, and with the 5 to 20 meter spatial resolution, spectral resolution will be helpful in crop monitoring. then with a temporal resolution of 6 to 25 days. That is the thing. So with this information, I am moving on to our topic that is rice monitoring. So here, so you know the national rice statistics. You are the much fit expertise than me. And here in Tamil Nadu, we are growing rice in around 19 lakh hectares, 1.9 to 2 million hectares per year. So Tamil Nadu is having a lot of seasons around. We have different sets of seasons, 16 seasons, but we have grouped them into 3 categories. That is the first season called Kurvai, then Samba, then the Navarai, 3 seasons. So Samba is the major season, which starts from August to the harvest is happening place during the January. So mostly these areas are irrigated with the canals or tanks. So so our major monitoring system also copes up with the Samba rice, and we are also giving the real-time information on Kurvai as well as Navarai also. So this rice crop in Tamil Nadu is vulnerable to many of the weather extreme events or natural calamities, because Tamil Nadu being located in the coastal region, it is vulnerable to flood, cyclone, as well as the drought also. So drought also, which is a common phenomena. So 2016 drought was a severe one. And floods, we get almost once in 4 years, severe floods are happening in the coastal districts, which affects mainly the rice crop. So during cyclone also, heavy rains are happening. That is one way causing flood. On the other way, due to winds, if the cyclones are happening in the later stages, lot of lodging in the case of maturity stage. Last year it has happened. Unseasonal rainfall, can call it in weather extreme events. So unseasonal rainfall at the maturity stage causing lot of damages by way of lodging or submergence. So these are major concerns we are having in the system. So to cater the needs on to protect these farmers from these calamities, we are going for 2 types of social protection measures. One is the relief from the government or disaster agency. Then another one is the crop insurance. So to cater the needs, we monitor very precisely all this information in a time series manner. That is, throughout the crop growth period, we continuously monitor the crop. So how this Sentinel-1A? So our major research activities now, we are focusing on Sentinel-1A based. Other satellite sensors also, if you are interested, I will briefly explain where we are using and other things. So here this Sentinel-1A, it is having a 200 kilometer swath, 200 by 200 kilometer is the one scene. So Tamil Nadu is covered by 8 scenes in 2 passes. This is track 92, then track 165 in 2 scenes. So one scene of satellite data, it is having around 1 GB data. That is in 20 meter resolution. If you go at 5 meter resolution, even very precise information can be achieved for each and every field. But one scene of data, it is 7 GB. So our monitoring system, we should have robust hardware as well as the software to process this much voluminous data. So TNA has established such labs, crop monitoring and disaster labs to cater these requirements. So we have 2 types of polarization, that is VV and VH. These are 2 types of data within the same satellite sensor, and which is acquired in two resolution, 5 meter and SLC data and 20 meter GRD data. So now Sentinel-1B is also available. So mostly it crosses over midnight, and it is it is irrespective of sunlight is there or not, it will cover the information very precisely. That is the advantage what we are having with the microwave satellite. So this is how we are monitoring the entire crop growth period using the satellite data set. These are the periodicity of observation. So this is flooding, means agronomic flooding, what we mean. So pre-flooding, flooding, then crop establishment stages, pre-flowering, flowering, then grain filling, harvest, even post-harvest. So normally the planting in Tamil Nadu, it takes place during the month of the peak. So planting is happening in the month of September, October. But some in the coastal areas, where they are going for long duration varieties of CR1009 or CR sub-1. So they are taking up the planting a little bit early during August. So we acquire the satellite data from August 15th to then the harvest is happening during January, and it little extends up to first week of February. So till that date, we are acquiring the satellite data. That means we are acquiring the satellite data at 13 to 15 passes during the crop growth period, and we stake them and analyze the data for achieving our different interpretation. So this is the methodology what we are using in the rice area mapping. So here we are acquiring the synthetic aperture radar satellite data. From that we are generating the sigma naught images using the now many softwares are available. Even with the ESA, European Space Agency, we have open source tool called SNAP. Then technically there is commercial softwares, 4 or 5 softwares are available. One is Mapscape from SARScape, that is SARR Map Switzerland. Another one, this is AgriX, AGRE, AgriX SARR from, it is an Indian company. So many company, but in case of, even though many companies are available on many data set analysis, for microwave only limited softwares are available, because the analysis and interpretation in microwave is a little complicated, but you need not worry about that, because this software, all this processing changes into automated processing system. So any scientist who is working in rice, he can get into the system quickly. Earlier, when we were taking up initial days of remote sensing, we used to do all these 9 steps of processing individually, one by one. So first one, grouping the images, then mosaicing. So in one pass, there are four images are there. We have to group them. Then we have to mosaic them in two paths are there. So we have to mosaic them. Then we have to co-register them, filtering, geocoding, then ANLD filtering, finally coming out with the process data. But all this data now it has been automated. So once you select the area, give the date from this date to this date, it will automatically do the pre-processing. So these are the pre-processing steps. Then from this, the output is the radar backscattering coefficient. That is the factor, that is dB in terms of decibel. And that is the one which discriminates different objects. Each and every object at different stages, at different varieties, they have differential backscattering signature as well as the backscattering coefficient. Then from that we are generating the leaf area index, and here the relative growth rate is also measured. Here the innovativeness what we have done, rightly pointed out by our respected director, Indian Institute of Rice Research, that now in the crop monitoring, 2 different aspects are being taken care of in crop monitoring and yield estimation. One is the remote sensing aspect, another one is the modeling aspect. So the models generally either Orisa, DSAR or ABSIM, all these models are a point-based model. They can simulate the yield for a particular point, particular location, if you feed all the values, whether variety, soil management. So, but now we need the information spatially. So we should earlier the approach of even National Crop Forecasting Center is to get this yield estimated in 5 or 6 locations, then average it, multiply with the area in that district, coming out with the production statistics, not the yield statistics. So now the scene is changing. It is the need of the hour. We should estimate the yield spatially for field by field. In case of crop insurance, it is for the entire village, village by village. Village is the insurance unit. So the spatial information or spatial yield estimation is the need of the hour. So here what we have done, we have integrated the remote sensing products with the crop growth model. That is the innovation what we have done. So the remote sensing data products, it will give you the backscattering, that is the variation in varieties or crop growth, everything. Then we can generate the leaf area index from that. Then third one, we generate the start of the season and end of the season. So you get the duration. So these inputs are integrated with the spatial data sets created on weather. So in Tamil Nadu, we are having 385 automatic weather stations owned by TNA. Then we have another 500 stations from PWD, 40 stations from IMD. So we integrate all this weather data and make it into a spatial data set. So here to assess the yield on spatial scale, remote sensing data is on a spatial one, that is in the map format. Like that, we have to generate different layers of information. So first one, weather, or otherwise, if you are not having a very good very precise weather data or good number of weather stations, we can use the satellite derived weather products. For example, rainfall, we are having the CHIRPS product. For the entire weather data set, we have NASA power. So we can integrate the data set from that if you are not having this weather data on real time with the automatic weather station. Kindly excuse me, this only this basic principle I am explaining it in detail. Then application we can just see. That is what I am taking a little bit time. Then the varietal information. So for each and every variety, those who are working in the model, we know we have to develop the genetic coefficient of that variety. Genetic coefficient means nothing but we are generating different growth parameters. For example, leaf type, leaf area, leaf weight, like that. Then the biomass, but all these things for a particular variety, duration, emergence, all these things. For varieties, we are generating the genetic coefficient. How we are integrating these things? It is generally through the AgroMet project, Agriculture Meteorology Project, Network Project. They are developing the genetic coefficients for different varieties, for different crops across the country. So here in Tamil Nadu, the Agroclimatic Research Center, they have generated the genetic coefficient for leading varieties of Tamil Nadu that we are integrating. Then the soil information. So we have TNA remote sensing has already developed the soil map at 1:50,000. So we are injecting all the soil parameter spatially. So then the last one, management practice. What are all the management practices? That we generally go with collect the information from crop production guide through the ground truthing. We collect the information. So what is the practice? What is the planting system? For example, is it direct seeded or transplanted rice ecosystem? And transplanted rice. In case of ecosystem, is it rain-fed or lowland or upland? All these things. Then the management practices. That is the seed rate to fertilizer application, pest and disease management. All these things we make the files in a spatial manner, and we integrate with the remote sensing product. And finally, through an interface, we are estimating the yield spatially. So for each and every pixel. So it is very simple. The model estimates the yield for one simulation for one place. We make this model to run umpteen numbers of time for each and every pixel. Then it comes out with the yield estimation spatially based on the spatial variability. Then we can also do the in-season forecast. Then end of season estimate, yield estimate. This is again validated with the CC crop cutting experiments. And finally, we come out with the maps and statistics and share it with the stakeholders. So this is the background. So in general, our idea is to generate crop statistics, that is the crop area. Seasonality means start of the season. Each and every pixel, what is the planting date and the progress. We can see the progress of planting. Then technology means if we divide it into stages, then we can generate what is the stage of the crop prevailing in. For example, how much area has come to maturity, so that we can push the machineries, harvesting machineries, like that. So with this information, we can also develop the machineries information system also. Like the Swiggy app, we can develop it for, because rice is the one crop, the most of the research efforts are being put in, not only in crop management, varieties, Now, for even the instrument mechanization also, rice is the one crop which has been almost 100% mechanized. So like that, even in insurance, 85% of the farmers, insured farmers are rice farmers. So like that, rice is the major crop. Because of that, we started our research in 2012 onwards to develop the information system for rice. So like that, we can extrapolate it to different crops with different models. So DSAT, it has many 28 models. So for rice itself, DSAT is having model, and SARR rice is there, SARR maize, SARR sorghum for maize and sorghum, then peanut grow, cotton, all these things we can integrate. But the principle is same. We are generating the spatial products and we are integrating it with the crop growth model. So large area monitoring, we do it with the satellite data. Location specific monitoring with the UAV, that is unmanned aerial vehicle, that is the drones with the multispectral and the thermal vision. So we can detect the moisture stress, nutrient deficiencies, pest and disease, and we are also assessing the impact of flood and drought. And this information can be passed on for mitigation strategies. Then we can develop the, we can pass on to the, if total failure happens, pass on the information to the crop insurance. So it is the comprehensive information system what we are developing and passing it to the stakeholders of farmers, extension officials, insurers, traders, and the policymakers. So coming to the technical details, these are the applications. So how we are generating? We are acquiring 13-day data and putting it into the state. So we are arranging one over the other, and this is the false color composite in the Kaveri Delta region. So you can see the blue or cyan ones are the rice fields. These are the black ones are the water bodies. These are also canals but covered with the plantations. So the plantations will be having much brighter pixels. So here these are coconut plantation. These are forest vegetation in the hilly area. Then these much little lighter, but compared to crops, which is brighter pixels, are the urban areas, settlements. This is Tiruchirappalli town, Tanjavur, other smaller towns, even villages you can see here and there, the brighter pixel. So these are small villages. If you zoom it, you can see all these things. So here the crop, this is rice. These yellow ones are cotton. These orange ones are maize. And these are tank. This is Viranam tank. This is another, that is Wellington tank. Then you can see these are this area. This is coconut, cashew nut plantation. So like that, these things which by my experience I am telling. So this has to be technically, these pixels have to be classified precisely as to the class which it belongs. For example, rice pixel has to be classified as rice. So how we are doing it? How we are segregating these pixels based on the backscattering. So each and every crop has its own backscattering property that I have already explained. Here you see the rice crop. So this is the agronomic flooding time. So where we get to the minimum backscattering value. That means it is in the range of -23 to -24. Once the crop emerges, then that value, dB value, it gets increased. It is in the -1 to -23. So it gets increased, and the variations we observe. So during, what is the primary variation during the peak vegetative growing phase, and once the heading happens, there will be smoothness in the surface of the crop canopy, that you have to visualize on a spatial manner, not a single plant. On a spatial manner, there will be surface smoothing, because you have to think at 20 meter by 20 meter as one pixel, not individual plants. Then once the heading happens, so once the heading happens, it will start declining. This is the peculiar backscattering signature of rice crop. So here in case of maize, if you see the variation in dB, within this, each point is 12 days. These are the different dates of acquisition. 1, 2, 3, 4, 5, 6, 7, like that. So from this, we can capture the start of the season. So this is the point where the planting has happened or crop emergence has happened. So from that, we can assess the progress of planting all this. So from that, for each and every pass, what is the progression? So we are using very many statistical features, that is called multi-temporal features, and integrating them, we classify the pixels. So this should be the minimum, this should be the primary variation, this should be the maximum, and the duration, all these things combine it, and we classify the pixels into rice. So like that, for maize, if you take in the initial 2 passes, you can see the quantum jump in and the backscattering values. That is the one. So, and in the tasseling, you get a dip. That is the peculiar phenomenon in maize. Whereas in case of cotton, it is almost static. In case of maize, it starts declining. So like that, each and every crop, here you see in black gram and green gram. So black gram, it is a very short duration crop. During 40 to 45th day, once the flowering happens, the decline is very sharp. Whereas in case of green gram, it is smooth and declines. So this is the difference between black gram and green gram. Whereas in case of plantation, you take coconut, it is static. The surface roughness, it is not changed because of rainfall or irrigation or other thing. Almost it is uniform. Here it is almost minus 14.5. So if you give that value across the different satellite paths, you can easily pick out the coconut pixels. It is very easy to differentiate the plantations. Only in case of the field crops, these points, these phenomena has to be taken care before going for classification of this. So once we give all these parameters into the software, but one thing is, even though the softwares are available, only the agriculture scientists or agronomists, they can apply their local knowledge. It is the domain knowledge is much important in coming out with the remote sensing product. That is why I readily agreed to address the group of rice scientists working in the working across the country, because the satellite data remote sensing, we can undergo training, we can get the software. Now with the advancement in the software, we can easily come out with the pre-processing. Earlier days, this pre-processing, we need the technical knowledge on remote sensing. Very high technical knowledge was the requirement. But now with the automated processing chain, the application part and the domain knowledge is very much important in classifying these crops and other things. So these are based on this signature. Now we segregate the pixels. This is the rice pixels, rice area. So we group them. This is the rice area map. And based on the start of the season, we can map it as a normal rice, late rice, as well as early rice. Late rice and early rice, how it happens? That is, in case of long duration crop, we go for early rice. Whereas in case of double cropping situation, where there is a little overlapping between the crops are there. So the first crop will start planting happens in May and harvested in October. Then the second crop, that is during the samba season, it is taken up little late, the last week of October or the first weeks of November. So those crops we can segregate. And this is the entire rice area map. And then this is the start of the season. So each and every pixel we get the start of the season. So from that we can group them, how much, what is the progress of planting in the first 12 days. Then the next increment of every 12 days, what is the progress of planting that can be acquired using the administrative boundary at a different level. So at state level, this one district, at block level, village level. And if you have the clear-cut cadastral maps, you can get it at the individual farm level, survey number level or farm level, or for a particular lat-long value, we can pick up the signature. For example, you are conducting the multi-location trial across the country. So you know where these multi-location trials are laid out. You can continue sitting in Hyderabad, you can monitor whether this planting in, for example, 1000 ALT or multi-location trials are there, FLDs are there. In ICAR-IIRR, FLD is the major component. So whether the planting has happened, whether the growth is normal, and whether the harvesting happened. Then what is the yield we can estimate. But in case of individual fields, for entire state, entire country, we have to estimate, then only we can pick up individually. or otherwise at least this will give you a better monitoring mechanism. That is one way. So we can see the progress of planting or start of the season from the satellite derived product. Then we assess the accuracy. Accuracy is the main factor in deciding the quality of any remote sensing product. We should have strong ground truth collection, and we should have strong training data set. So we collect the ground truth and we use it for mapping a part. Then a part is used for validation. So the accuracy should be more than 85%. Then only any remote sensing product can be used by the stakeholders. So for rice area, we are getting an accuracy of 92 to 95%. If it is contiguous area, sure 95% we can easily achieve. In case of sparse crops, we can get around 88 to 93%. That is the thing. For rice, we have very clear-cut methodology, and it has been proved again and again. And we can come out with the rice area, start of the season, and the monitoring mechanism. So how do we monitor the crop growth? So we are generating the leaf area index. So lot of research has taken place in the field of remote sensing, linking the backscattering values with the leaf area index. And I will share we have published one article how it is worked out. Leaf area index is estimated from the backscattering value of the rice crop. So this is the leaf area index. You can see wherever this is during the 2016 where the drought has occurred. So you can see wherever the good crop is there, you can see the values. Good crop means even with the stress, but it is comparatively good. The values are more than 3 to 4 like that. Then in case of total failure, the red ones, you can see the values are less than 1. So how these failures are happening, especially during 2016. So immediate with the rains, they have taken up sowing because the water was not available in the dam. So the farmers were advised to go for direct seeding of rice. So with the rains, they have taken up sowing, but immediately after 25 to 30 days, the crop failed because of the dry spells, intermittent dry spells in many places. Then in fewer places, the rainfall was sufficient. Then in later date, some water was released for a shorter duration. So in those areas, the harvesting has happened, the crop growth was there, and you can see the leaf area index in those areas. So these areas where the crops have almost completely failed. So this phenomena, one we use for monitoring, another one we pass on to the crop insurance. I will tell how it is used for crop insurance at later. Then comes the other parameter. This is with the microwave data. The other one is the NDVA. It is correlated to the greenness of the crop. That is greenness, and the next step is biomass. So you can see the complete failure in these areas. Here also the effect was very high, but here we have used the satellite data with the 20-meter resolution. Here it is 250-meter resolution. Because of that, you will get generalized picture. So only in this area the crop was good. Okay, here also this is the Kadalur, 4 blocks of Kadalur where they have adequate borewell water. So when you go with the high resolution satellite data, that is 5 meter to 20 meter, you can even more precisely assess the damage. Here you can see. So you can segregate even within here, as if it looks like the entire area is very good. But if you see closely, here also there are moisture stress. Okay. So these are the 2 phenomena which is used for monitoring the crop condition. So for example, if we are coming out with the rice monitoring system for the entire country, or you take it for East Coast. So what is the general condition? What is the progress of planting? What is the general condition? You can assess in a preliminary stage using the NDVA, that is the general greenness, and and you can also, if you foresee moisture stress, you can also use the NDWA. That is normalized differential vegetation index. then normalized differential water index, then leaf area index. These two will give us the idea. Okay, these are all the area where the crop is failing or facing the moisture stress. There we can suggest the mitigation strategies. For example, TNA has come out with the PPFM, that is a bacteria, pink pigmented facultative methanoid bacteria, which is capable of keeping the crop green for another 15 days, even during moisture stress conditions. So we can go for our other mitigation strategies. We have a lot of anti-transparent and other agronomic practices to keep the crop green or live. So these strategies, we can identify the area and push the agronomic practices in that area. So that is the advantage here. Then comes the yield estimation. So here, this is for 2016. So these are the yield levels. Only in fewer places where they were having bore wells or supplementary water resources, the crop was good, but in many cases, it was totally failed. No yield, and even the yields were in the range of 1,000 to 2,000. And we have the threshold yield for each and every district. For all the in case of Samba, around 12,000 villages are growing rice. So threshold yield. So we can compare what is the deviation from the threshold yield. That is also one strategy. So this is the yield, and we can, if you zoom it at the village level, at even at the individual survey number level, we can get to the information. So this is during the 2018, where the crop was good in the Kaveri Delta. The water was the storage in Metru Reservoir, which is dependent on the rains on Karnataka. The water level was good, and the crop, you can see the entire delta, the yield levels are from 4 to 5 tons. You can see only in fewer places little lesser yield, or maybe they may be of double crop area where the short duration crop is planted and the yield levels are little lesser. But in case of Ramnath district, where we go for semi-dry rice cultivation, the seeds are sown under rainfed condition, and it comes up with the rainfall. And once the storage in the tanks, so in this Ramnath, Sivaganga and Pudukkottai, we have many tanks to capture the water, and these tanks are used for, tank water is used for irrigation, supplemental irrigation for the crop. So once the crop is, the storage is good, the crop condition will be good. But that year, the rainfall was failure, but the storage in reservoir in the Kaveri Delta was good. The yield was good. Whereas here, you can see the crop failure and the greater yield reductions. That is the, and it depends upon the water storage in each and every tank. So this is how we are estimating the yield and using it for different purposes. And this is the one, the varietal spread. This is not the one which is directly detected from satellite image. This is the one which has been collected from the ground-based information. So for example, in the crop insurance, we are conducting around 7 million CCs across the country. So in Tamil Nadu, around 200,000 CCs are conducted across the state, and we are given with the access to all this data. So from that, in that, while collecting, we are using the CC app. In that, we are giving information on system of planting, the crop, variety, system of planting, irrigations, stress if any, pest and disease, nutrient, all these things we collect. From that, we can generate a lot of information. So if we get access to this data across many states, definitely we can come out with the preliminary rice variety map. And we have also detected the penetration of our recent variety in how many villages we have assessed. Around in 1,800 villages, the presence of Co51 was noticed. So one thing, we can assess the variety. So here we have given only, okay, it is not for the entire rice. We have given the spread of only TNA rice variety. So on the other hand, the BPT, it accounts for around 36% of the rice area grown. This was the strategy 3 years ago. Now TNA has come out with the replacement for BPT, which is taken care and which is spreading in a faster rate. So, so varietal spread. This is one way of using GIS. We can map that. The other way is 1 minute. This is the one. So we can use the hyperspectral remote sensing because so within the variety, if we observe the variation only in one band, it is difficult to segregate the varieties. But in hyperspectral remote sensing, what we are using thousands of wavebands. So for example, here we have used from 350 to 400 to 1000 nanometer with 382 bands. So each and every variety has its own reflectance in each band, variation in each band. So we can easily detect. You see, we have assessed for around 300 genotypes. Here I have selected only a few, maybe 30 or 20. I think. So you can see the variation between the varieties. This is the individual varieties. Earlier I was showing the generalized signature in the SARR data, that is in the waveband of 5.23 centimeter, only one waveband. So here to discriminate the varieties, we have to use this type of hyperspectral remote sensing. So we are using, this is one thing. Another one, we have the hyperspectral imaging sensor from 350 to 2500 nanometer, in which we are using more than 1000 bands to segregate the thing. So once we are using this one, definitely we can segregate the variety as well as genotype. So we should have it. For example, we can use it in the drone-based sensor, drone-based imaging sensor. Now, this European Space Agency, it is coming out with a satellite called NMAP, and with that we can collect the hyperspectral. So at present in Indian remote sensing ISRO, we don't have these hyperspectral satellite, but it is in the offer. So it will come in the coming years. So definitely we can come out with the varietal information. Then the pest and disease. Mostly the question put forth to the remote sensing persons in agriculture field is, can you monitor the pest and disease incident? Definitely we can monitor. You can see the difference we can create, and with the analysis is also a major part. So earlier we were finding it very difficult to. So for one band we are putting forth that much effort. Here we are using 300 bands with umpty numbers of varieties. So larger data sets, complex analysis. But now with the availability of deep learning tools, it has become much easier. In one stroke we can come out. So yes, in the near future we can map the varietal distribution for the not only for rice crop, any crop we can do it. So this is the drone image of a genotype experimental field. So from the image, one thing is backscattering. Another one, you can assess the health, NDVA, NDW. Many indices are there. So we have developed a tool called HyperAnalyst, in which you can generate 36 indices. So normally the breeders are going for the other way of analyzing the properties of the varieties. So here we are doing it with the ground-based real-time spectral variability within these genotypes. So there are we have developed 36 tools comprising 36 indices. So that means using the variability in the near infrared, then the changes. This is called red edge. This is red, then this is green. This is in the blue region. So 600 to 700, it is called red region. The transformation from red to near infrared, it is called the red edge. The variation here also, here the slope, many things we can capture. In green also, the ratio. So like that, many indices have been developed that can be used to discriminate the variety. Then comes the crop cutting experiment. So we can minimize the number of samples crop cutting experiments using this geospatial technology. It is widely used in crop insurance. So with the geospatial technology based methodology, or TNA smart sampling methodology, we have come out with the result that 50% of the CCs can be reduced. because the state government is investing around 1,200 crores in taking the CCE data, crop cutting experiment, conducting crop cutting experiment. They have recruited 750 personnel and they are spending money like anything in coming up with this. But with the satellite data, it is very, very cheaper, one thing. On the other way, even for conducting crop cutting experiment, we can use the satellite data and we can minimize the sampling points. That is, we can come out with the optimized sampling methodology. So in the contiguous area, we can reduce the number of samples. In heterogeneity, we can increase the number of samples like that. Then this is the one area where we have a lot of potential, because this rice crop information is needed for settling the crop insurance, because this crop is vulnerable to weather extreme events wherever it is grown, either in the Indo-Gangetic plains or in the areas which is vulnerable for floods and the drought, rainfall in the initial stages, droughts, then in the East Coast region, susceptibility to cyclones and heavy rains, and also drought. So these crops are this rice crop is subjected to lot of weather extreme events. So the insurance is also, in insurance also, rice plays a vital role. Around 80% in Tamil Nadu, 80% of the farmers, insured farmers, are rice growing farmers. So how do we? There are many parameters: prevented sowing, failed sowing, unaccount payment, CC based compensation, and okay, I will complete in another 10 minutes, even though I have many slides. So different features, we have developed different products to cater the needs. So we can go for the crop insurance scheme completely with the support of remote sensing data. That's what happening in Tamil Nadu. Tamil Nadu has declared the remote sensing based crop insurance in 2016 onwards. So for the last 5 years, we are supporting the state government with the regular data as an operational service. And we are charging it with the insurance company. We are generating revenue also. That is there. So in 2016-17 and 17-18 itself, with our technology, 5 lakh farmers were benefited. Every year, our technology, on an average, it helps minimum 200,000 farmers in the state in getting the benefit one way or the other. So the claim settled during that period, it was 2,400 crores. Tamil Nadu ranks second in getting the insurance claims across the country. It is the one reason behind is the use of technology. So this is how, so at village level, we can get to the information of the area zone every 12 days interval, and we can come out with the prevented sowing area. This is the failed sowing. This is a normal signature, normal crop. This is a failed crop in 24 days. So we can, within the village, how much area failed at how much duration, 24 days, 48 days, the good crop, everything, good crop to poor crop, we can come out with the ratio. Because in insurance, if the 75% of the crop in that village is failed due to failed sowing, then it is declared. So these are the villages, number of villages, districts used our data, and the number of farmers benefited. And the other aspect is the monitoring the tanks, water resources, the water spread and its influence on the crop growth. So here you see this is the tank. So in the initial date, for this point you can see the backscattering. It is less than 0.20 minus 24. That means the water is there throughout the period. So this is the area newly filled in with the water. So we can assess the spread, the area. Volume, now we are coming out with the methodology that is a 3D terrain mapping, so that we can come out with the shape in 3D using the drone and the high resolution imageries, and we will be coming out with the water resource information for the tanks. For the dams, we have the information. So this is the good crop happened in that area. You can see the crop is very good. The water was available throughout the period. Yes.
Pazhanivelan sir, not able to hear you.
Yes, sir. Yes, sir. Now I am.
Okay.
So do you see my screen? Sir, do you see the presentation?
Yes, sir. Yes, sir. Go ahead, sir.
So this is the disaster impact, assessing the impact of disaster. So this one is the flood map. You can see the new already existing water bodies, black ones, and the newly inundated or flooded areas that we can very precisely, we can say at 98.5 or 99% accuracy level, because this SAR data, micro data is highly sensitive to moisture. So we can precisely assess the area inundated. And this is the drought. In 2016 drought, you can see the red ones are the complete crop failure, and this is the cyclone damage where we have used drone images. You can see the uprooted trees. So we have assessed the trees, that is around 38 lakh trees were uprooted or damaged, coconut trees. So that was the information which was used by the government in pushing the relief. So this is the comparison of NDVI during the November, that is the peak growing season. I can see that 2016 it was worst year. 2020-21 was the good year, but the floods happened. After that, because of Nivar cyclone, floods happened. These are the inundated. In case of flood, we assess three things. One is the inundated area, and we combine the information on the crop stages. So here the crop is at maturity stage, inundated. Here the crop is at vegetative stage, and the setback was there and then recovered. So here there was not much, slight the water might have drained immediately. So based on this, you can see these are the inundated area, but even within that, the red ones are the young crop of less than 24 days, which were completely inundated, 2,500 hectares only. Even though the total area affected was 30,000 hectares, around 2,500 hectares was completely inundated or submerged. So those information can be precisely. So here this is the drone image. You can see the standing crop as well as the large crop. You can see the large fields here. The standing within the field, how much area is large, that can be precisely assessed. So the next one is the spatial estimation of methane emission, because the paddy fields accounts for more than 30% of the methane emission. So we have integrated the different satellite data sets. So we have used the MODIS and the Landsat thermal images to assess that is land surface temperature, because this methanogenic bacteria is the activity is directly correlated to the surface temperature. And then the period of flooding from our micro data, the duration of the crop and the period of flooding. Then we have integrated the DNDC model, which is a biogeochemical model, and we have come out with the spatial estimation of methane emission. So it was in the range of around 20 gigagram, and it is well within the IPCC prescribed limits. And with the DNDC, we can also assess the daily emission rates. So and the peak also. So this peak can be correlated with the atmospheric methane flux, which is again detected by using a Japanese satellite called GOSAT. So so we are also monitoring the impact of this emission and this contribution to the methane flux in the atmosphere. So these are very detailed studies. I need not get into that. So we validate this data with the field chambers. That is a normal methodology adopted. Using GC, we analyze the gas. So we assess the rate of emission as well as the quantity of methane emitted from the paddy fields. And this is for other crops. I just rushed through. So like rice, here we have integrated the DSAT model, SARR maize for maize, and we have come out with the maize area and yield map. So here in the yield, we got an accuracy of around 90%, 87 to 90%. And these are the area maps at the block, village level, we can generate. Here for groundnut, this is the area map. and this is the genetic coefficient. So wherever we don't have sufficient data on genetic coefficient, we conduct the field experiment and come out with the genetic coefficient. This is the weather file which we have generated using the NASA power satellite derived data set for the spatial estimation of yield. These are the ground truth points, and this is the yield. And we can also assess the potential yield as well as the yield gap, and we can come out with the factors responsible for the yield gap, and then we can go for our frontline demonstration in an effective way. So wherever the yield gap is very high, those districts we can select, and we can push our agronomists or other scientists in the ICAR program to demonstrate the recent varieties and other technologies. And this is for the other plantations, cashew, mango, banana. So now this is pixel based classification. Now we are moving for object based classification. We can identify the individual trees. Individual trees come out with the number of trees also. Even now we are extending it to the yield estimation in horticulture crops, mainly the fruit crops. We can detect the fruit. This is the Sapota image, drone image. We using this e-cognition tool and the deep learning, that is AI based tool, we can detect the fruits. So we are developing the methodology for yield estimation to support the farmers in getting due prices. This is the one, the high density planting of mango. We are continuously taking the images using drones and assessing the canopy growth at 3 months interval. We are monitoring, and the space wherever the saplings died, that area, that locations we identify and communicate to the horticulturists. This is our soil resource information center. So we have done the soil mapping at 1:50,000 scale. Now we have moved on to digital soil mapping, integrating the profile information. We have profile information for 6,000 profiles across the state. Using machine learning tools, we integrate the satellite derived variables with the profile information, and we are coming out with the digital soil mapping. So, here using this map, in the conventional map, you will get one value for the entire polygon. Here you can get for each and every 30 meter. If you click, you can get new information. That spatial variability we are capturing, and we are using it for now. It will facilitate us for farm level agro technology transfer, nutrient management, and other things. So this is the digitization where we have done for around 2,500 village individual farm boundaries that we are having it. This is the cadastral level nutrient mapping, village level nutrient mapping using GIS. We have used the samples of the soil health card scheme, and we have come out with the mobile app called TNA Soil Doc. It is available in the Google Play Store. So in a click, we have integrated all these maps into the system, and in a click, you can get the soil parameters. That is soil series, then all the physicochemical properties, pH, EC, organic carbon, bulk density, nutrients, and the hydraulic properties. Then we have also integrated the constraints, that is salinity, alkalinity. These are the limitations we have included. So wherever in a click, you can come to know whether your farm is having any such limitation. Then we integrate with the agronomic recommendations. What should we do? And we have also, this is with the already established data sets. So in case of nutrients, we have to do it at least once in 3 years. It is a dynamic property. But the other data, these land constraints and other things, which doesn't change much. Once in 10 years, data is enough. But if you are very much interested, you can you can analyze the sample fresh and feed the values and get your recommendation. And we have also mapped the locations of soil testing labs across the state, so that the farmer can click and get his nearest route map for the nearest soil testing laboratory. And you can also feed the lat long value and get your information. Or sitting in Hyderabad, you can select the village, select the farm, demonstrated field farm, and get the soil data. That is it. So this is the rainfed area map, salt affected area map. Then this it is pertinent to rainfed area, the length of growing period, and the crop planning. So we have done it for the last 20 years. You can see the changes. Green ones means the length of growing period is more than 100 to 150 days, but it is getting declined. You see now it is changing. So in 2001, 80% of the area, 78% of the croplands in Tamil Nadu, rain-fed lands in Tamil Nadu was having the length of growing period of 100 to 150 days, but it has come down to 35% now. So this is water resource monitoring. We are developing the spatial agriculture information platform for the entire state, integrating all this information. Then the drone capabilities. These are the different types of drones we have. This is the copter type. This is a fixed wing. This can fly up to a height of 1 kilometer and go up to the range of 16 kilometer. It can go and come. That is the thing. And we can cover large area, 40 square kilometer in one day. Then this is the spraying drone with 16-liter tank capacity and 3.5 liter fuel capacity. It can fly. The endurance is 3 hours. With the batteries, we can fly only for 15 to 20 minutes. These drones with batteries, it can fly 30 to 40 minutes, 60 to 70 minutes. So this is the drone applications what we are doing. Mapping and monitoring. This one, you can see the takeoff of it flies at a speed of 85 to 130 kilometers. And it can see once it takes position, then it will cover the area. We can map the area, it will cover, it will take the image with 60 to 70% overlapping so that we can generate 3D information also. You can see the. So this one is the spraying drone. So the spraying drones can cover 1 acre in 2 to 10 minutes, depending upon our spray volume what we fix. And the nozzles, they are capable of, we use different 2 types of nozzles, atomizer and so that is we can deliver 8 liters to 23 liters in 1 minute time. That is the thing. And the height we can maintain from 2 meter from the surface to 20 meter we can go. And in case of canopies, we can maintain even up to, if it is uniform, we can maintain 0.5 meter or otherwise 1 to 2 meter that we can. So here you can see the herbicide applied plot. This is non-selective. So you see the applied plot and the not applied control plot, 98% accuracy. That is uniformity in spraying can be achieved in case of herbicides. We have demonstrated for that is for pre-emergence, post-emergence, and non-selective. And we have formed a big team of 18 scientists under my leadership that from different disciplines to standardize the drone protocols for smart delivery of inputs. So this is the crop health monitoring using these drones. So we can go for phenotype evaluation. You see, this is cotton crop. This is ours. In the genotypes, you can evaluate select the phenotypes. So many literatures are there. If any plant breeder is interested, I will explain to them in person. So these are other applications of drones, fall armyworm spraying. So this is the granular application. So you can direct seeding of rice, we can test it with that. So it can spread 0.5 to 5 mm thickness. Any granule we can adjust and we can make it useful. So this is micronutrient in tomato fields, spraying organics like Panchakavya. So we get a lot of support from the state government. State government has notified through GO, and we have made it in the school textbook also. That is on use of remote sensing as well as insurances to create awareness among the young generation based on the instruction from our agriculture secretary. So these are the accomplishments. So we have a lot of funding opportunities. Those who wish to take up research, they can approach many things, state departments, DST, National Geospatial Program, Geospatial Technologies. So I am also one of the expert committee member in the National Geospatial Program, and DST, National Spatial Data Infrastructure, SEED Program, DBT, many bilateral programs are there. National Disaster Management Authority, Ministry of Water Resources, National Hydrology Project, which is having a lot of funds, and we are doing the ET and soil moisture assessment for the National Hydrology Project, and we have the covariance flux tower also, and we are doing the infiltration rate for the entire state under this National Hydrology Project, and the National Crop Forecasting Center, ICAR-IIRR, we can target as a group. Then NRSC, Space Application Center, Response Program is there. So many funding opportunities are there for those who want to work in this innovative field, and you can also get trained. So we are offering 121 days program. Actually, we planned it for February because of this COVID. We have postponed to, it is going to be conducted in person. We are going to organize it during the month of May. So if anyone is interested, we are ready to. So thank you. The application of GA is limited only by the imagination of those who use it. Thank you.
Respected Pazhanivelan sir, thank you very much, sir. Excellent presentation, and you are also your talk you are made it to our rice applications. Thank you very much, sir. Now I request our DVK Nageshwar Rao to initiate the question answer session, sir, for only 5 to 10 minutes, sir. Then we can wind up, sir, after closing remarks of our director. Thank you, sir. Very elaborative lecture. Now, DVK, are you there, DVK? Go ahead.
Yes, sir. I am very well here.
Okay.
Can you hear me?
Yes, yes. Go ahead. Go ahead.
Sir, it is really an excellent presentation covering, an array of, resolutions, first of all, right from 250 meters to say centimeter level. That means from MODIs to your drones. It's really, an excellent application context where you have shown, the different kinds of applications, including the greatest, what is that, Prime Minister's, Fasal Bima Yojana, where you are really doing, excellent job in, selecting the, what you call, the crop conditions for crop insurance. It's really an excellent, because you have shown how the technology can be used to serve the society of the nation. It's an excellent application. In fact, I myself have, in fact, it is with reference to the cost of establishment of your laboratory and operational cost, because though you have so many free and open sources of software and data, but you must have invested something initially, including manpower and all. That is one question. Second thing is that, do you do anything on phenology metrics using time series analysis and all, other than MODIS data? Because MODIS, anyhow, it is freely available, and it is but with 250 meters resolution, so it has its own limitation. Because definitely I understand that for variety differences, other than hyperspectral remote sensing, there must be something like time series analysis with all the phenology metrics like seasonality indices and all. And third question is, you said about periodicity. Are you sure that you get all the images during your that particular periodicity schedules? I think you are using only the synthetic aperture radar data, not visible spectrum. So these three are my questions. Please answer this so that I can monitor the other questions by other people.
So the establishment of lab now, it is not much costly. So we can invest on few computers. Even for server, you need not have it. You can use the cloud space. So establishment is easy, and only the software we have to come out with the good quality software. So it costs a little bit. Other than that, we can establish the lab within a very less budget. That is one thing. Regarding this phenotype studies, we can use the drone images. Drone images, because we are going to evaluate it within the field or in a smaller area. So we can use the drone images. We have done one study, we have initiated, but the that student, he got selected for PhD in the same area because of his expertise. He got selected for Washington State University. He moved on, but now we are helping the breeders to use these things. That is one thing. Then the other, we are using only the microwave because during the cropping season, the only solution is to go for microwave. You will not get any cloud-free data. If at all, means only modis data. So that can be used for general reference. In case of, in that case, you have to use the drones. You have to fly the drones below the clouds, get to the optical, because optical data has its own strength, that you can get many parameters, direct relationship of the plants, including chlorophyll content, chlorophyll A, B, total chlorophyll, greenness, the water content, all these things can be achieved. So for experiment purpose, we can use the drones. Even for large area monitoring, now we are planning to use a swarm of drones. So that is there. So the technology of integrating mobile data, mobile observation is also now taking a vital role. So mobile data, mobile images, drones, then the satellite data. We have to integrate all these things. Whichever is cheaper, whichever is easily available, then we can come out with the monitoring system.
Sir, whether you are offering any training in e-cognition for a short time, like?
In our training program, we will also cover e-cognition. 21 days we have the e-cognition software. Now, sir, you are from ICAR-IIRR only, sir, headquarters only.
Yes, sir. Yes, sir. In fact, I am here for the last 5 years. Earlier, I was working in different organizations.
Okay.
And I received my first training from NRSC 92. Okay. So I am in this line, something like that.
Now it is available in PJTSC, that is Telangana State Agriculture Institute.
Yeah. But anyhow, we need some training, sir, since it is objective.
So you are open, sir, at any point of time you can contact and you can come over and learn it, no problem. Or a structured program, no problem.
Yes, sure. Sir, we have one question from Dr. Brajendra. So he wanted to know whether NDVI and spectral images can be able to quantify the nutrient status in the soils. This is a question from our soil scientist in this institute, Dr. Brajendra.
We cannot, we can correlate to some extent only the nitrogen, not the other, this thing. Phosphorus, we can, but if you use, it is not in the NDVI. If we, for example, potassium, we can assess with the waveband of 2000, I think 2543 or 443. So for each and every element, there are specific wavebands. If you formulate, if you come out with the sensor, if you come out with the instrument which is having that specific sensor, we can go for specific nutrient monitoring. But still, organic carbon and nitrogen are having the best correlations with the reflectance. The others, it is not yet established. You can go for sensors.
So there is one question from Dr. Praharaj from IAPR Kanpur, sir. Dr. Praharaj, you may raise the question.
Thank you, sir. Thank you very much. I am thankful to Dr. Palani with a very good, interesting topic, sir. Actually, sir, I am interested in pulses, particularly black gram and green gram are grown in your area and mostly in southern parts. Besides that, we have also some of the major crops, for example, the chickpea, pigeon pea, other sorts are grown. Now, our problem is we don't have a model, good models working on particular these pulses. And I don't find, sir, because it's a rice-based topic, we don't find anything on pulses. But you have some experience on pulses. So is it possible, sir? And most happily, sir, my student, rather my junior colleague, Dr. Munalini CG, joining as a PhD student in TNTNU. And she is very much having some expertise in remote sensing, and you will be helping her. We are shortly going to have a MOU signing. So, sir, is it helpful? You can have some outsourcing, maybe some software is required for these pulses, particularly area mapping and yield estimation point of view. Thank you.
Yes, sure, sir. Already we have developed the methodology for black gram and green gram, which is a major pulse crops here in our region, and the models. We have, for example, chickpea, we have the specific model. So with that idea only, we have formulated my student thesis in that area, that is for the eastern UP, that Bundelkhand region, mapping the chickpea, then the monitoring of chickpea, coming out with the yield gap analysis for chickpea using TSAT crop growth model, integrating this this data. So definitely, once this she gets all the permissions, definitely we can do the mapping. For mapping, we will guide her. She can do it from there itself. That is it.
Thank you, sir.
So as of now, I see only these are the questions. I don't know. I mean, no chat box question, no hand raising. I guess I think Dr. Mahendra is interested to ask some question. Dr. Mahendra.
Sir, Pazhanivelan sir, very excellent presentation, sir. Really, what I heard earlier is different from what I today heard from you. It was more practical, and it is very useful for our rice research. We have three things we wanted to do, sir, in future. Then where we require your help. First is varietal spread across the country. At least what are the varieties that are spread across the country? That is one aspect. Then second thing is we wanted to see the yield gap analysis in different ecosystems. That is second aspect. Then greenhouse gas emissions, because many of the cropping systems, especially in rice, they are shifting towards DSR. And we are also collaborating with many NGOs and others where they are also working with very big area where it is DSR has been converted. So I request your, I think all these things can be done by hearing your lecture. Then we need your suggestions and our training, whatever it may be. That is only my humble submission, sir. If anything is there, you can clarify now. Thank you, sir. Thank you very much.
Thank you, sir. These things can be done by mutual discussions in the later part.
Okay,
Sure.
sir. Thank you.
Sir, there is one more question from our Dr. Brajendra. So he was writing, sir, I have another query. Is that image-based and sensor-based nutrient detection techniques are how far correlating with wet-based chemical estimations?
I couldn't follow, sir.
Dr. Brajendra, can you raise your question directly? Because some spellings are confusing.
First of all, very impressive lecture, sir. Congratulations to you. I want to know, there are many agri startups have come up recently, and they are throwing their techniques in estimation of moisture. Even your TNAU Coimbatore Sugar Computing Research Institute also, they have established sensor-based that moisture estimation methodology. Along with other agri startups also have come up. They are telling that sensor-based nutrient assays such as available nitrogen, phosphorus, potassium, other micronutrient and secondary nutrient estimations they can do. I want to know, in our traditional laboratories, where bit-based chemical methodology is followed. So how far this physical method of sensor-based, image-based detection techniques is correlating with our weight-based chemical methodology, which is being largely followed across India in traditional laboratories. This is what was my queries.
So there are many startups coming. They import many sensors from Chinese firms across the country. Even we have 2-3 companies we are working. But the correlation between the analysis, that is the sensor-based and the lab analytics, has to be done. The elaborate study has to be done, and the correlation has to be worked out. These studies, it has to be taken up in a long term to standardize the things. But there are sensors, but we should come out with the methodology. We should be convincing to the scientists as well as the farmers. So that for that we need a lot of research work. So under NASF, TNA is having 2 research projects on developing the handheld or on-the-go sensors to come out with the nitrate. So most of this methodology, if it is plant-based, then these imaging techniques will work very nicely. If it is soil-based, then a lot of work studies have to be taken up.
Sir, there is one question from Dr. Aruna Mohan. So she was asking, if students are given such mapping work, can you give any opportunity to work in this line, whether it is for free or in paid mode? This is the question from Dr. Aruna Mohan from Karaikal.
So students means they can come here and work for project work by paying rupees 10,000. It's very nominal for their project work. Other than that, if the institute is sponsoring, sending some scientists, means that is some mutual agreement, and it's on scientific cooperation basis.
So one question from our colleague, Dr. Gopinath. So he was asking that, can we use radio spectrophotometer, soil data and satellite data for soil mapping?
So this I have already explained, sir. This spectroradiometry is a field-based instrument. We are using it to validate the satellite-based images. So only we have done a lot of work in this aspect, and we have established correlation only for organic carbon and nitrogen. Other than that, a lot of investigations, even more wavebands, complex indices are required.
So as of now, these are the questions, sir. Participants, any more questions? I think no, as of now. So back to Dr. Mahendra.
Dr. D.V. Kanageshwarao, thank you very much for nicely organizing this question and answer session. Thank you very much. Now I request our Honorable Director, Dr. R.M. Sundaram, for his valuable closing remarks, sir. Dr. Sundaram, sir.
Yeah. Thank you very much, Dr. Pazhanivelan. It's indeed an eye-opening presentation for a novice like me, who is more bothered about cloning genes or using molecular markers. Your field is equally, or even if not more important, in terms of the impact what it has created. And I'm sure that with experts like you and also good teachers like you, what I liked is you took very good pains to explain each and every step of whatever you have been doing very nicely, sir. And it was indeed a very nice presentation. I'm sure that with experts like you, the field is going to bloom, and we'll also contact you for work, some kind of work which you can do at pan-India level. My colleague, Dr. Sailaja, and also Dr. Mahendra Kumar, they will contact you, sir. I have just one small query, like the same based on spectral imaging, can we forecast pest and diseases also, sir, in outbreaks?
Yes, sir. With drones, it is easy to do. With the satellites, satellite data and the weather data, we can do the modeling. We can forecast them. But with the drones, we can precisely identify the area and give the information or recommendation, and through the mobile app, it can be integrated.
Say, for example, there is a major disease called as bacterial blight, which occurs in Godavari Delta area year after year. And there are also other diseases. Of course, for bacterial blight, there is no plant protection measures. Only growing resistant varieties is the only solution. But there are other diseases like blast and also sheet blight. If timely protection measures can be taken up, the spread can be minimized, or they can even be avoided, sir. So I was just wondering, is there any satellite-based solution for us to forecast outbreak of these diseases, or monitor the outbreak of some of the major diseases or pests, and then give some very quick solutions to farmers? Just a...
This is an area where the Department of Remote Sensing is working with the Agroclimatic Research Center and the plant protection scientists, and working with the state government on a digital agriculture initiative. So definitely we can come out, sir. For any specific diseases, if you say, then we can take the image, analyze, and come out with the model. That is one thing, sir. And one more, I've forgotten to mention, sir. From this year onwards, for the first time in India, we are offering PhD remote sensing in agriculture. That is the thing. Anyone who is interested, that is the eligibility is soil science, agriculture meteorology, and agriculture physics, besides remote sensing. So any scientist who wish to do PhD, they can take up and they can do their research work there, and they can contribute to the system.
Thank you, sir. I believe just like phenomics in biotechnology, I think supraphenomics, wherein using satellite data, if it is possible for us to dig out more and more information about crop plots or experimental plots, particularly our ACRIP plots, if we are able to dig out additional information, I think that will be an upcoming field, and we can actually combine that with ground truth data and then make accurate prediction models regarding how the ACRIP trials are conducted, and then what are all the barest minimum factors that are responsible for increasing production, sir. Thank you. Your presentation was wonderful, sir. And we are really grateful to you on behalf of ICAR-IIRR and also on behalf of our Society for Advancement of Rice Research. Thank you very much, sir.
Thank you, sir. Thanks for the opportunity given and the interest shown in this field of innovation. Thank you, sir.
Thank you, sir.
Thank you very much, sir, Sundaramjit, and very valuable conclusions. Let me thank Pazhanivelan once again for your excellent talk, sir. And moreover, sir is coming during third week, and we can have one short meeting with Pazhanivelan so that we can discuss some of our rice research issues, and then he can also collaborate with us in many projects, in coming projects. That is only, I think he is visiting PJTSU very soon, sir. So he will be, we will have that opportunity also in coming.
Sir,
correct, sir. Pazhanivelan, sir.
Yeah. Sir, kindly spare at least half a day to visit our institute. We can have a mini meeting here also, sir. It'll be our pleasure, certainly.
Thanks.
Sir, once again, I thank you one and all. And now, farmer vote of thanks. I request my colleague, Dr. Soumya Saha, to propose formal vote of thanks.
Sir, before that, Dr. Volati, as President SARR, if he has any comments, we would like to hear.
Sir, Volati, sir. Or any other, I think I have seen Balchandran, sir. Many are there. If anything you want to.
I think let's first hear from Dr. Volati. Any closing?
Volati, sir.
Thank you very much for the very informative lecture from Dr. Pazhanivelan. Actually, this remote sensing, I have seen in ICAR-IIRR, Dr. Keshwar Reddy time, Dr. Keshwar Reddy, Dr. Muralidharan, Dr. K.V. Rao, all these people have contributed at the field level. And it has come a long way. And it has come to, from the basics to the applied aspects, it has come. And the speaker has covered so well the advancements in remote sensing. And it was quite an interesting historical development, which I could really realize what developments have taken place. But when it comes to the ground level, as the director, Meenakshi Sundaram, was also pointing out, for the diseases prediction and others, for most of the diseases or even the soil deficiency symptoms, the plants will have to develop certain amount, that is maybe say 10%, 20%, 30%. Then only the spectral signatures are going to vary. So what is the minimal base level for which these spectral signatures will be changing in the coming days in the field? This is what is to be assessed for a accurate prediction and the application part of it. This is what is going to be in the coming new generations. That is what I feel from the developments what have been taking place. And I really compliment the speaker for his excellent presentation. Thank you very much for giving me this opportunity to speak about it. But one particular part which he, as a biotechnologist and the genetist, also should look into, the phenotyping and the genotyping in the biotechnology, it is going on. And similarly, phenotyping is going on from the remote sensing. Can we able to really make a connection between these two?
That was
this
exactly
is
my suggestion also.
We should look at.
That's exactly.
So, thank you very much.
Any other, I think, want to share their views? If nobody is coming forward, then I request my colleague, Dr. Soumya Saha, to say formal vote of thanks. Saha, it is yours.
Thank you, sir. Thank you. It is my immense pleasure, and on behalf of the entire RICE family, and especially from Indian Institute of Rice Research, and on my own behalf, I'm highly privileged to get this opportunity to propose a vote of thanks. And first of all, I want to express my heartfelt gratitude to the honorable today's speaker, Dr. S. Pazhanivelan sir, to enlighten us on this topic at rice area mapping and use of remote sensing products and other tools for crop growth models also. And I think as our other valued participants already told, that it may be the future of monitoring as well as different prediction models and other aspects in agriculture especially. So it has a huge future in this topic, and I congratulate him and thanks for his valued talk in this interesting topic, and also thanking him for addressing all the queries raised by the participants from different parts of India. Then I want to thank our director, Indian Institute of Rice Research, Dr. R.M. Sundaram sir, for always encouraging us to take up this kind of topics for this as a part of Azadi Ka Amrut Mahotsav, and being a part of the seminar committee of ICAR-IIRR, I find his interest in conducting such kind of lectures in the webinars. And I thank Dr. S.R. Voleti sir, our former director in charge, for his active participation in this webinar and raising his own queries. I also want to thank Dr. R. Mahendra Kumar, who is Secretary of Society of Advancement of Rice Research, for readily agreeing, and actually he only invited Dr. Pazhanivelan for this topic, and he along with Indian Institute of Rice Research, the Society of Advancement of Rice Research, we are jointly organizing this webinar series. And I also want to thank the other valued participants like Dr. P.C. Rao, members of SARR, and all the IIRR scientists and other participants from ICRIP Rice family, and also to AKMU team, which is led by Dr. B. Sailaja, for smooth conducting of this event. Dr. A.P. Padma Kumari Madam, the chairperson of the seminar committee, for successful arrangement of this webinar. And thanks are also due to Mr. Yadaya and Sravani for various arrangement in the committee room. And last but not the least, all the participants, which are indeed the valued listener and their patient hearing and contributing for the enrichment of the webinar. And especially my thanks to Dr. D.V.K. Nageshwar Rao sir for giving his remarks and enriching the discussion part and raising the queries of the participants. And thanks one and all. Thank you, sir.
Thank you, Amit sir. Thank you.
Thank you, one and all, sir. Once again, we'll be in touch with you, sir, Pazhanivelan sir. And now today's webinar is closed now. Thank you, one and all, for your
Thank you.
patience. Thank you.